Morning, folks. So our exam is going to be on Friday, and we'll review that today. I'm going to go over all the topics that we have. And if you have particular questions about topics, then we can look at some questions about those topics. There's a lot to cover. So, also, I just want to give you a heads up about the final. The final is cumulative, and the final is taken from your 4 exams. So if you want to start preparing over the Thanksgiving break, some of you might want to do that because, you know, that's the kind of people y'all are. Then you can just start looking at the 4 exams from this semester. That's the best way to study for that. I'll pull questions from those exams. I'll change the numbers. I'll change sort of the context of them. But if there's material that's not on those 4 exams, it won't be on the final. And the best way to study for it is to start with those 4 exams. We'll talk more about that when we return after the Thanksgiving break. All right? You have any big plans for Thanksgiving? You going home? Yeah. We're going camping, I think. The weather looks good, but cold. And I think my son and I, we are going to do this bike trip to Morgan City. Morgan City! Woo, woo. Yeah. But we're going to ride to Morgan City and stay overnight and then ride back. He's excited. He's 10. When you're 10, man, you get excited about all sorts of stuff. Man? Are you running across 9? No, we're going to go up Highway 1. Yeah. No, bicycle. I'm not taking 90 yards. All right. All right. So lots on this exam, y'all. It's chapters 7, 8, and 9, and 10. 7, 8, 9, and 10. 8, 9, and 10. You're right. 8, 9, and 10. All right. Chapter 8 was on. It was sort of the second chapter on rotation. So you're going to see torques. Let's see. I start the recording here. Again, I'm not going to be here on Thursday, unfortunately. But if you have really pressing questions, I get back from the zoo at like 2:30. So if I really need to, I can come in and meet with you. But we're not having a help session. Okay? So, but if you need to meet me, we can do so. I can make that happen. So with torques, you need to be able to find the net torque. Those are those problems, you know, where we have a bar and it's rotating about some axis and I have these forces that are acting on it. Be able to find the net torque. If that's a problem for you, we'll come back. We can work through a problem like that in a bit. You need to be able to find, okay, I guess that's about it. The net torque. You might also have to rank the torques like we did in the concept test where we had the list of those things and I said which of these torques is greatest, which is least. That's like finding the net torque as well. Moment of inertia. You need to be able to find the moment of inertia for a system of particles. You know, that's like those problems where we have the particles that are all rotating about an axis of rotation. You need to be able to find the moment of inertia for a particular object, like for example a cylinder or a sphere or a bar or any of those things that are on that table. Make sure you print out your equation sheet. Don't bring it to the test. I'll give you an equation sheet, but print it out, paste it to your refrigerator, wherever you look, and just be familiar with it, with what's on there. And all those equations for moment of inertia are on there. Also be able to rank your moments of inertia. We had some problems like this in the concept test, so be able to rank from least to greatest or whatever. Rank your moments of inertia. And remember, moment of inertia in its basic form is the sum of mr squared. So when you're ranking moments of inertia, you are figuring out which has the most mass at the biggest radius. We can look at some problems like that in a little bit if you like. You need to know all your units, all that stuff. I think they're all okay with that. You need to be able to apply Newton's second law. We've worked through a number of problems like this. These are those problems where you say the torque is equal to I times alpha, and then out of that might come any number of things. I could, so for example, let's say I have a bar. It has forces acting on it like this. You would first need to find the net torque, then you would need to find the moment of inertia, and then you would find the angular acceleration, which is going to be torque over I. That's from Newton's second law. And then you might have to do some simple kinematics calculation to find the angular velocity or the distance that it travels in a certain amount of time. Or I might also ask you to find the kinetic energy at a particular time. something like that. We've worked through several problems like that. If you look back at the old test, you'll find a problem similar to that, or more than that. 1 or 2 or 3 problems like that on every test that's on this chapter. All right, so be able to use the Newton's second law. Kinetic energy will be wrapped up in that. Nothing terribly complicated, just knowing that kinetic energy is 1/2 I omega squared. And then similarly, we had angular momentum is L is equal to I omega. Now we did have a series of questions in the concept test that worked with kinetic energy and angular momentum, and if this one has half the moment of inertia, what is its kinetic energy, how is that affected? You might want to look back at those concept tests in general, but also at that series of questions about that, about kinetic energy and angular momentum and how they're related. And then also with the angular momentum, we had conservation of angular momentum, where if I change I, then omega has to change, or if I change omega, I has to change. Yeah, like the figure skater, when she pulls in her arms, it makes her go faster. So be able to work those problems for conservation of momentum. A little bit of everything on this test, so it's going to be a lot to look over. No power. You don't see any power in the test. Okay, we'll come back to this. If you have questions that are particular, we can look at those. All right, that was all chapter 8. Chapter 9 was on solids and fluids. Lots in chapter 9 too. We had the states of matter. Make sure you know your states of matter, but you've known those since first grade, so you should be okay. Also, don't forget, liquid or fluids are things that flow, so that includes liquids and gases, right? So fluids are sort of a subset of the states of matter that includes anything that flows. Elastic properties, elasticity. This was that Young's modulus thing. If I apply a stress, I get a strain. So stress is proportional to strain. That is, if I pull on something, your equation is on the equation sheet. But if I apply a force per unit area, that's going to cause something to change, delta L over L. So if I have an object that is this length L, and then I apply a force per unit area to it, it's going to make it get longer. And it'll make it get longer by this distance, delta L. Just make sure that you work through 1 or 2 of these problems, or that you're familiar with working through them. Being aware that this delta L here is a change in length. It's not your new length, but it's your change in length. That's sort of the tricky part of that, is realizing what that delta L is. That it's not a new length, it's actually the extra length that you add on to that object. All right? We work through several like that. You'll also see density and pressure. And these are, let's do pressure first. We had several things with pressure. That is, finding the pressure at a particular depth. That's a certain depth, h. And we said that that pressure is equal to P naught plus rho GH, where P naught is this pressure here. Be careful with your units. That's going to be sort of a sticky thing in this test. Be careful with your units, because the pressure will always need to be in Pascals for this calculation. In fact, your pressures always need to be in SI units. Is there any case where it's not true? No, it always needs to be in SI units for Pascals, but sometimes I will give you the units in atmospheres, because you know atmospheres is just a common unit for pressure. So if your units are in atmospheres, you'll need to convert that into Pascals. All right, so just be careful with your units. We also saw pressure in measuring pressure. In measuring pressure, we used a manometer. And remember, our equation here was a little bit different from the one above, and it was that P is equal to P naught plus or minus rho GH. So let's say that I have a pressure over here, P. I want to know what this pressure is. And this pressure over here is P naught. And the difference in these two levels is H. And this is the density of whatever fluid is inside this tube, inside this manometer tube. Be careful with this because you want to make sure that you use the right either plus or minus here. What would I use here, plus or minus? Which one is bigger, P or P naught? Which pressure is bigger? P naught is bigger here, so that means I'm going to need to use the minus because P naught is bigger than P, so P naught is P naught, or excuse me, P is P naught minus whatever this term is, rho GH.
So P is always bigger.
No, not always. I mean, you could have it, in fact, usually P naught is smaller, but you could have it also where the levels are like this, right? In that case, P naught would be less than P if the levels were switched. Just be careful of that. Make sure that you look at it and tell, well, gosh, are these pressures, how are they different? Which one's bigger? Maddie?
Okay, so if P is bigger than P naught, we use the plus.
Well, if P is bigger than P naught, if this number is bigger than this number, then yeah, you have to use the plus. If this number is smaller than this number, then you have to use the minus. You can, it has to be that way, right? Because if this one's bigger than this one, then I have to add something to it to make it bigger because these two sides are equal. Once you see it, I mean, it sounds complicated putting it in words, but once you do it one or two times, I think you'll find that you're pretty good at it. All right. Also, don't forget your density. Your density definition is the density as mass over volume, although that problem will likely be wrapped up in an Archimedes principle problem, so I'll hold off on that in just a second. All right. Or you could just see a basic density problem, give you the mass, give you the density, ask what the volume is, or something vice versa. Do be careful because, on previous tests I've put all the constants like on the test. Not all of them, but some of them have been on the test. But I haven't done that on this test, so you need to make sure that you have your equation sheet and that you have all your densities on there, you have all your coefficients of linear expansion, your Young's modulus, all that business is on that equation sheet. Okay, so if there's a value in your problem that you think, gosh, I need some more information, don't forget that equation sheet because there's a lot of information on that. Okay? All right. Then Pascal's principle. We have three big principles, right? We have Pascal's, Archimedes, the continuity equation. Actually, we have four. Sorry. And we also had Bernoulli's principle. You need to know just basic ideas about what these are, just the definitions. Remember, Pascal's principle said that any change in pressure in a fluid is felt throughout. That's what makes hydraulic lifts possible. And you will have one of those hydraulic problems where I have two different pistons, I have a certain force here, a certain force over here. Depending upon what the areas are, the forces will be different. Okay, so you will have to do one of those, but you also need to know just the basic idea behind Pascal's principle is that any change in pressure over here is felt over here. And it's just because our areas are different that we get different forces out, because remember, pressure is force over area. Archimedes' principle is based on this idea that the buoyant force equals the weight of the displaced fluid. And so we work problems, for example, if you just have an object that's fully submerged, the buoyant force, it has two forces acting on it, the buoyant force and the weight. And we can find the buoyant force is equal to the density of the fluid, the volume of the object, or the submerged volume of the object. If it's not completely submerged, then it's just a portion of it will be submerged, and it'll be that portion that's submerged times the acceleration due to gravity, and that'll tell us what the buoyant force is. Remember that if this thing is floating, that the buoyant force is equal to the weight. Because if it's not accelerating up or down, then your net force is equal to 0, and your buoyant force will be equal to your weight. So that's Archimedes' principle. The continuity equation is based on the conservation of matter. This is that A1 V1 equals A2 V2. It says that if I have a pipe, for example, I have a certain amount of fluid flowing through here, I'm going to have that same amount of fluid flowing through here. But because it gets bigger over here, it gets to go slower because I don't need to push the same amount of fluid out. I have the same volume flow rate here as I do here. And as a result of that, because this has a greater area, the speed is going to be smaller. And that comes about here in this equation. All right, you'll have to apply this equation to solve for a speed, but then you also need to know what the continuity equation is based on and what it means. It's based on the conservation of matter. You have this constant flow rate, volume flow rate. Bernoulli's principle, oh, so by the way, here, I would have a low speed here and a high speed here. Bernoulli's principle is based on the conservation of energy. It says that any amount of energy that this fluid has over on this side, it also has to have that amount of energy over here on this side. Now on your equation sheet, your Bernoulli's principle looks like this. It's like 1/2 rho v squared plus pressure plus rho gh. We're not going to be using this at all. That just means if your pipe actually changes height, but we're not going to do that. So the big takeaway with this is, as we talked about in class, is that V goes up, the speed of your fluid goes up, then the pressure is going to go down. If V goes up, the pressure goes down. And we had a couple applications of that in the class. You can go back and look at the concept tests and some of your in-class questions. You'll see some similar ones to that. Okay, I know this is fast. Any questions? Things where I've lost you? We'll come back and revisit all these things. Not right now? Okay. So that was Bernoulli's principle. Archimedes. Remember, with Archimedes, you might also have to calculate the density of something along the way. That's it for chapter 9. And then chapter 10 is the shortest of the 3 chapters. We don't have a whole lot in chapter 10. We have temperature scales, we have linear expansion, and we have ideal gas law. So in chapter 10, temperature scales, you need to know what are the temperature scales. Goodness, bless you. Are you done now? Okay. My wife has like the loudest sneeze. Or she doesn't anymore, actually stifles or sneezes. But a bunch of years ago, I don't know, 8, 9, 10 years ago, she was sneezing. I never said anything about it. She sneezed in the car. I was like, it's really, it hurt my ears. It was just the right frequency, too. But now, like, she was upset for a little bit because I told her that she sneezed too loud, but now she's okay with it. And she just sort of stifles them a little bit. But she doesn't like to stifle her sneezes. She likes to just let them out, right? Y'all too? You feel better after a good sneeze, right? All right, so temperature scales, you need to know what they're based on. Remember, your Celsius and your Fahrenheit are based on those freezing and boiling points of water. And your, what's the other one? Oh, the Kelvin scale is based on absolute zero and the triple point of water. So you could see a question, like we've seen in the quick tests and old tests and stuff, where I ask you a question sort of probing your knowledge about that, what they're based on. You also need to know how they differ, right? So the Celsius and the Kelvin scales have the same size degree. 1 degree Kelvin is equal, or 1 Kelvin is equal to 1 degree Celsius, a change in temperature. Whereas the Fahrenheit, the degree is a lot smaller. You also need to know those basic temperatures. I might give you a conversion problem where you have to convert one temperature to another. You have the equations, but for the Celsius Fahrenheit, it's just good to know sort of rough equivalents. So, you know, this room is about 20 degrees Celsius. Outside on a sort of summer day is about 30 degrees Celsius or a little higher. All right. Then linear expansion. You heat something up, it gets bigger. We're just doing linear expansion, although it does expand to area and volume expansion, but we'll just deal with linear expansion. That is, if I heat something that's one direction length, it'll get a longer length. So we had several questions in class and in your homework about linear expansion. I would expect both a calculation and then also a conceptual question about this, of the same strain as what we've done in the homework and of what you've done in the concept test. Nothing about molar mass. I think I told you this, but nothing about molar mass on the test. Though you will need to use the, you will need to like the number of moles for certain things, but you don't have to use the molar mass at all. We just spent a little bit of time on that, but you're not going to see it on the test. And then ideal gas law is the last thing. I'm sure y'all are pretty well equipped with the ideal gas law. You've probably used it quite a bit, but it's just that the pressure times the volume is equal to N times R times T. Just let me remind you of your units, because that's going to be sort of where you're messing up. The units for pressure needs to be in Pascals. That's the SI unit. Though often it's given in, atmospheres. The unit for volume needs to be cubic meters, though often it's given in liters. I'll give you the conversion factor if that's the case, if you need to convert from liters to meters cubed. N is number of moles, that's always number of moles. R is on your equation sheet. And T, which is often given in Celsius, needs to be in Kelvin. So you might have to do some unit conversions. I try not to do too many mindless unit conversions, but sometimes we use units that aren't in the SI system fairly commonly, and this is one of those cases. So you might have to do some unit conversions. Just make sure, in general, it's always safe to have everything in SI units. So, especially for the ideal gas law, it's required to be in SI units. So you have to calculate some things, and then you'll have some questions like we had in class where, if you keep one of these constant, like if N and T are constant, and P goes up, what happens to V? Well, V is going to go down. That sort of thing. We had several questions like that on the concept test, so I would look over that before the test on Friday. I think that's it. All right. Any particular questions?
I was working on an old test. I think it was from 2014, and it was a hydraulic system, and asked for the weight of the truck, and I was really confused. Like, now.
This one? Okay.
So it asked for the weight, so it asked for like the force.
Right. Well, the weight is the force. So if it's able to lift up this truck, then that is the force.
I was thinking like force weight equals mass. I think like the mass is amazing.
No. So here, it's asking for the weight of the truck, and if F2 is pointing up, this is F2, FW is pointing down, so F2 is going to equal the weight. The way that you do this, by the way, is you'd say F1 over A1. I know this isn't what you're asking. Equals F2 over A2, and you will have a... Yeah, don't think too much about it. So F1 is, well, what was the answer? B?
Yeah, B.
So it's 10,000. F1 is 100 over A1, 0.01, equals F2, which we want to know, over A2, which is 1 meter squared. And then you solve that for F2. All right? Lindsay?
Can you go over number 8 and number 15 on fall 2013?
Is this okay, Abby?
Yeah.
Okay.
And I also like one other question.
Okay, let's go ahead. Exam 5?
Yes.
8 and 13? Okay, this is a similar problem. It was a little more complicated because you had to blow it up. This is fall 13, exam 5. This is a lift problem. The thing we had to do here was we had to find the area. And so that's what made it a little more involved, is you have to find the area. So F1 over A1 equals F2 over A2. This is going to be F1. This is R1, so we'll need to find the area. This is going to be R2, and then the force that we're looking for is F2. So F1 is equal to 15,000. A1 is pi times R1 squared. equals to F2 pi R2 squared, which is 0.04 squared. The pi's cancel, and I solve that for F2. Or, excuse me, R1 was 0.2 meters. Let's go and put that in. If I solve that for F2, do you know what the right answer was by chance? Do you doubt that?
I don't know, because like in the video, like the 15,000
Let me.
F2, I don't know, I was confused.
Oh, okay. I'm sorry. Let me just double check this. Yeah, I get 600. So F2 is equal to, if I cross multiply this times this, and then divide by 0.2 squared, I get 600 newtons. It looks like this. My figure looks like this. I have 0.2. My radius over here is 0.2 meters. My radius over here, it's a cylinder, is 0.04 meters. And then I have 15,000 newtons coming out here. And then I have 600 newtons coming in here. Is that clear now? I'm sorry if that was unclear on the video. And what was the other one? 15. Can I clear this one, y'all? You're going to see all this. You'll have a Pascal's principle problem. 15.
Like, you didn't do any math, you just kind of like said it was, I don't know, it was hard to, I didn't get it.
Okay, do I just sort of wave my hands? Okay, let's see. So, this, I have a pipe, it's flowing at 6. Okay, it's, let me check everything, something happened. Okay, it's flowing at 6 meters per second, 0.5 centimeters, and then it goes to a second pipe with 1.5 centimeters. You know, it looks like it should be a Bernoulli principle problem because it has all that density and stuff in it and pressures, but it's not, because all I really need to know is the speed. I'm going through a 0.5 centimeter pipe, and then I go to a 1.5 centimeter pipe, or the radius here is 1.5 centimeters. And I have a velocity here of 6 meters per second. And now I want to know, what is the velocity here? Well, the first thing I know is that it has to be smaller, right? Because I've gone to a bigger pipe. So my speed has to be smaller. So I'm going to get rid of C and D. Now, if you really wanted to go through and do the math, you would say A1 V1 equals A2 V2. A1 is going to be pi times 0.5 squared times V1, which is 6, equals pi times 1.5 squared times V, oh, I can write over there, times V2. But you don't really have to do that, because you see your radius gets bigger by a factor of 3. That means that your speed is going to drop by a factor of what? 9, or 3 squared, because our area goes up by a factor of 9 here. So that means my speed goes down by a factor of 9. My speed was 6, so now it's going to be 6/9, which is 2/3, which is A. So that's why I didn't do any math. You don't really have to if you can pick up the ratios. But if you want to, that's fine. And that's where you have to do this. So you would say pi times 1/2 squared times 6 equals pi times 1.5 squared times V2. Your pi's cancel. You solve that for V2. 0.5 squared times 6 divided by 1.5 squared. That should be equal to 0.67. Is that clear? But you will see a continuity equation like that for certain. I'll take this away. All right, what else, y'all? Yeah,
I
Alex?
have a question on another test.
Okay.
Fall 2011 exam 3. And number 17.
Made a 98.5 on my exam. My second exam in my Greek class. Like, that was good, right? 98.5. That's out of 100. Thank you, Maddie. I'm sorry, Annalise, what number were you?
Number 17.
17.
You started to work it out, but then you said you were going to go back to it.
Oh, really? Okay.
Yeah, I was confused too. So
That's confusing. Why would I do that? Okay, so here, I know that this pressure P is equal to rho GH plus P naught. This is a barometer. That means it's a special case when P naught is 0. It's a vacuum, right? So that's P naught is 0. So I'm just looking for P, which is rho GH. The column of mercury, the density of mercury is 13,600. That's on your equation sheet. G is 10. H is 1.2 meters. And so that gives me 163,000 pascals, which is 1.6 atmospheres. Remember, 1 atmosphere is 1 times 10 to the 5th, or 100,000 pascals. So 163,000 pascals is 1.6 atmospheres. I'm not sure why I skipped it. It's not a complicated problem. Yeah, Caitlin?
So one of the, I think it was a quick test in the workbook. He, like, you know, we saw for P and we got that.
Mm-hmm.
You used 1 times 10 to the 5th as, but is that like for a certain circumstance? Like you didn't solve.
Oh, yeah. So that was, yeah, I do know what you're talking about. So there was a problem where I just said you're at sea level or whatever, or something like that. But at sea level, your atmospheric pressure is 1 atmosphere.
Okay.
So right here, where we are, the pressure is 1 times 10 to the 5th.
Okay, so you'd always solve for this unless it said you were at sea level or something. Like you
Yeah.
solve for P this way, but if you were at sea level, you use 1 times 10 to the 5th. That's P.
P naught.
P naught. Okay.
or it's either.
Right.
So unless it's like the barometer, P naught is understood to be 1 times 10 to the 5th.
Okay,
Unless
so
it's given in the barometer.
no, not necessarily. So if she said so, is P naught always going to be 1 times 10 to the 5th unless otherwise stated? It'll be stated otherwise.
That's not like that's
Yeah,
not
don't worry, it'll be stated.
So when you're solving for pressure P, don't worry about that. But if
Right, don't worry about it.
But if you solve for higher numbers.
Right. Yes. Okay. Is that clear? Okay. All right. What else, y'all? Any other particular questions?
Yeah, did you explain how, you know what the P plus PO plus or minus rho GH?
Okay. So she asked about the P plus or minus rho GH. A lot of students get tripped up on this. I know we've already talked about it. Let's just sort of do it one more time. So in a manometer, which I use to measure pressure, I'm comparing one pressure on this side, we'll say this is P, to another pressure on another side. This is P naught. All right, so I have these two pressures that are different, and because they're different, I have a column H here. And the equation, which is on your equation sheet, is P equals P naught plus or minus rho GH. Now I know P naught. If I'm at 1 atmosphere, if I'm at sea level, P naught is equal to 1 atmosphere. But otherwise, I'll just tell you what P naught is. And then you have to figure out, well, gosh, do I use a plus or a minus? And so you need to look at this and say, is P bigger or smaller than P naught? In this case, P is bigger than P naught because it's pushing down, pushing this up. So I have a bigger force per unit area on this side. So since P is bigger than P naught, I have to use the plus sign right here. Because P is bigger than this number, so I have to add this extra number to it. If it was the other way around, if P was smaller than P naught, that is if my levels were switched like this, then I would use the minus sign because P would be less than P naught, and so you'd have to subtract some value from P naught to get P. All right? Okay, I'll just sort of scroll through. If you see anything, holler out. Pascals, we did all that. Pressures. Anything, y'all? You okay with chapter 8, 9, 10?
I'm not sure, because I only saw it a couple of days ago, but number 19 on Pascals 12, test 3, I'm not sure what it is, so I'm kind of curious, because I was part of what it is.
Okay.
Yeah, I don't, these are confusing.
People are very confused by these, so let's just take a minute. You aren't the only one that's confused. I've talked to several students. So on this one, you need to rank the moments of inertia from least to greatest, or from greatest to least. You will have one of these where you have to rank the moments of inertia. So what you have to do here is look for those objects where I have the most mass at the biggest radii. Because when I have mass out at big radii, because I have this r squared terms here, it's going to cause the moment of inertia to go up a lot. So here, first of all, I can tell which one has the least moment of inertia. The one that has the least moment of inertia is going to be A and B. In fact, A and B are the exact same here, right? Because it's just split on one side. So I'm looking now for one where A is equal to B. That's D, C, and B. So I can get rid of A, option A. And I can also get rid of option D, because I know that A and B have the smallest moments of inertia. So they should be at the end. So I can get rid of this one and this one. And then I can ask myself the question, which one has the biggest moment of inertia? Well, gosh, which one do you think it is, B or C? C has the bigger moment of inertia, because that's right, I have more mass out here at big radii than I do over here. Let me show you another one. Let's say that I have, well, we had this one in class. Let's say that I have two bars like this, equal length, equal mass bars. I can just draw a couple of axes, A or B. Which one of those axes, about which of those axes does it have the greatest moment of inertia? B, right, because if I go about axis A, this whole bar right here doesn't contribute anything to the moment of inertia because R is equal to 0. And here, my bar only goes out to half the total length of the bar for rotating about axis A. But if I'm rotating about axis B, I have this bar out at the greatest length that it could be, and then I also have this that's rotating about. So about axis B is going to be a whole lot harder to rotate than about axis A. It's like, doing this rotation versus doing a cartwheel. That's a lot harder because your moment of inertia is a lot bigger going about your hip. Or even harder is like rotating about your head, right? Can anybody rotate about their head? Maybe some of you can, but I can't. All right, let's say that I had one like this. Say I had a plate, and I have different axes of rotation. Say I have an axis right here, call this A, an axis right here, we'll call this B, an axis right here, we'll call that C, and an axis right here, call that D. Where this whole plate can rotate about in the page like this. So it's rotating either clockwise or counterclockwise in the plane of the page. Which one of those will have the least moment of inertia? D will have the least moment of inertia. That's right, because the radius here, R, the smallest, is only like half the width of the square. Which one has the biggest moment of inertia? B has the biggest moment of inertia because I have mass out here at a really long distance from B. And then in between, what about A and C? Which one of those is, they're the same? Right, so if I were to rank them from biggest to smallest, it would be B is greater than A is equal to C is greater than D. So once you do it a few times, hopefully it just sort of becomes intuitive to you that you're looking for these masses that are at big distances from the axis of rotation. But you will have to rank moments of inertia, and you have to calculate them. Good question. Is that your answer? Yeah. Lots of people are confused about that. So if you're confused, that's okay, because you're in good company. All right? What else, y'all? Have lots of tests this week? How many tests do you have written? You can't count your physics lab final. That doesn't count. That doesn't count as a test. That's like, you just go in. You don't have to study for it. You just go in and take it. 3 tests. Okay, I'm sorry. That's just sort of the way life is, okay? But I feel your pain. All right? Okay? I think that's... Any questions? All right, y'all. All right. Well, I will see y'all on Friday. We'll meet in the auditorium, okay? It could be cold in there, so bring a jacket.